I will probably finish a little early too, leaving us more time for the posters, for lunch, and for those of you who will go snorkeling and whale watching. I wish I could join you. Sorry. I'm going to continue my discussion of gravity on cosmic scales. First, let me summarize the main points of the first lecture so that you keep these in mind as I proceed through three lectures. First of all, if you were paying attention, you will notice that I designated two goals of observational cosmology. The first was to determine the matter density, or in fact the total energy density of the universe, by measuring the expansion history using the Friedmann equation. That is the standard technique that has been used for many years and underlies major cosmology projects. It is the goal of the supernova cosmology projects in their various forms, measurements of PAO, and so on. Of course, some of the measurements can do other things as well, but in terms of measuring distances, redshifts, or expansion history, the goal is to understand the composition of the universe. And it is from such measurements that we infer the existence of dark energy. But there is an alternative hypothesis that dark energy is not caused, that is, cosmic acceleration is not caused by an exotic substance, but perhaps by a modification of the Friedmann equation, and therefore modifications of general relativity. And so it behooves us to find tests of general relativity or other gravitation theories on cosmological distance scales. Now, I very purposely designated these as goals number 1 and number 3. What is goal number 2? Oh, nature effect. That is your homework assignment. It is to write down your choice for the second goal, or in fact, feel free to change the order, even drop some of mine, although you probably don't want to drop the first one, since an awful lot of funding is affiliated with that. But I would like people to think about the goals of observational cosmology. Make a note, and perhaps during one of the breaks we can assemble some of your answers and fill in the missing number 2.
And we can discuss this on Thursday.
And we can discuss this. This would be a fun thing to discuss on Thursday. Big picture question here. Okay, in the first lecture I talked about the evolution of cosmic perturbations, and I finished up with a discussion of cold-dark matter evolution. I pointed out that this commonly used equation is not at all obvious from the general relativity formulation in conformal Newtonian gauge. It turns out that this actually is equivalent to the relativistic formulation under a set of assumptions. First of all, one has to define what one means by the density perturbation. That's very important when working with general relativity, because that density perturbation in relativity comes from the component of a tensor, the energy momentum tensor. And components of tensors have no invariant meaning. They're dependent on the coordinate system that one uses. What one should do is to define the physical density measured in some Lorentz frame, for example, that at rest in the matter. And if one does so, then one obtains a density perturbation, a gauge invariant variable that is a combination of the variables I introduced last time. And one can write down the equation of motion for that gauge invariant density perturbation. Here I'm calling it delta sub m. In the previous lecture I called it nu for the number density perturbation. Well, this equation, as you probably know, in the Newtonian limit, assumes that the only force acting on dark matter particles is gravity. There are no pressure forces, for example, and it is only the gravity of the dark matter, because let's say the matter fields, dark matter and baryons, anything that clusters, because that's what produces this density perturbation on the right-hand side. And so for that to be self-consistent, one requires that pressure forces be negligible, or said another way, that the length scales of interest are much larger than the Jeans length. Moreover, because this is based on linear perturbation theory, the density perturbations have to be small. In practice, that means length scales larger than of order 10 megaparsecs for our universe. Maybe 50 megaparsecs, depending on the measurements one is making. But then one also has to think about possible clustering of dark energy. In a lambda CDM model, the cosmological constant is completely inert. It has no perturbations. In fact, we talked about this last time. There are no scalar perturbations of a lambda-dominated universe, a disturbed universe. However, if the dark energy is dynamical, a quintessence field or something else, then it will develop density perturbations also, and then this equation would need to be modified. I presented in the first lecture a general solution in the limit of long wavelengths anyway for the metric potentials or perturbations. And the nice thing about it is that these can be written in terms of the expansion history and the composition. Why the expansion history? Well, we see the A of tau and its logarithmic derivative with respect to conformal time here. The composition is implicit in this function alpha, which is proportional to 1 plus W times the background density. So if we know the background evolution of the universe, then we know how long wavelength density perturbations evolve, or in this case, gravitational potential perturbations. They are related by the Poisson equation. And so here, in fact, is the so-called growing mode of density perturbations for any background. And that's very nice. One can, of course, parameterize the solutions to this equation in numerous ways. And in my third lecture, I will talk about a parameterization introduced by Eric Linder. But it is also possible to work directly with the solutions to this equation, and there they are. One has to be a little careful with using this because, again, I showed last time that entropy perturbations and shear stress perturbations can modify the dynamics. While those are absent for cold dark matter, the dark energy could be exotic, and as many people have noted, may have shear stress perturbations or might even have entropy perturbations. The overall question which I formulated, and I want this to be one of the main lessons of my lectures, is that from measurements of the Hubble expansion history and the growth of density fluctuations, we do not have enough information to test general relativity or other theories of gravity. And you can see that just by counting the number of functions. There are two measured functions here. I'm ignoring the scale dependence by assuming we're in the long wavelength limit, where all the density fluctuations are growing at the same rate, so there's no gene stamping. The number of functions that we can measure in general relativity are, first of all, the dark energy composition. So implicit in this is the equation of state for dark energy. But then, as I just remarked, the dark energy might be exotic and have these further properties. So we have three functions, only two measurements. In principle, there's not enough information to solve the problem. And just to complicate things further, we also want to consider modifying gravity and ask, how can we then possibly constrain these different possibilities of exotic dark energy or modifying gravity? And that's what I'll be talking about a bit in this lecture and more in the third. So, some general references. Cosmological perturbation theory is not well developed for theories other than general relativity. Here are some general references to classes of alternative theories. The FMR theory, which I introduced last time, and about which I will say much more today. A couple of very nice review articles, extensive review articles. Scalar tensor theories, which have a very long history, going back to the late 1950s, and recently of great interest because of their resemblance to, in fact, equivalence to FMR theories. And then Tevis, or the relativistic formulation, Lagrangian formulation of Milgram's modified Newtonian dynamics. I'm not going to discuss this today, but I might discuss it in the third lecture. I think I'll take a vote at the end of this lecture. These references will give you lots of background into the topics, but there is no wholly complete or contained treatment of cosmological perturbations. It's a big challenge to do that, and I will try in this lecture to introduce some of the concepts to you, but still, this remains an unfinished subject. So now I'm going to discuss some work on cosmological perturbations and the general properties of F-bar theories. This is work that I'm doing with Alessandro Silvestri, who will be talking about some of the observational tests of these and other theories on Friday. So the F-bar theories are in some sense the simplest generalization of general relativity. If you consider the simplest expression of general relativity to be the Einstein-Hilbert action, so the Ricci scalar as a field, this involves derivatives of the metric. And if we write down this action integral, we have the action as a functional of the metric and of some matter fields, which I've just called psi here. These could be the standard model particles, for example. The metric is involved in this Lagrangian clearly in constructing, for example, kinetic terms of these fields. And all that the F-bar theories do is to add some other function of the Ricci scalar to the Einstein-Hilbert piece. As I remarked last time, if this is a quadratic term, then it's expected to be important in the early universe, and it could in fact drive inflation. Now, it's always important to ask in these theories, what physics governs the motion of matter? Does matter fall, does a test particle move along geodesics of the metric? That concept is so ingrained in general relativity that you might not think to ask the question. But as we will see, it is an important question for some of these theories. In this case, the modification of the action occurs only in the gravity term. There's no modification of the matter Lagrangian. And so if the dynamics of particles is free fall along geodesics in general relativity, then that will be unchanged in these theories. And that's good because it means that we can use, for example, the conventional motion of cold dark matter particles in cosmological simulations with this so-called coupling. As you may know, field equations can be obtained from these action functionals by varying the action with respect to the fields. And if you vary with respect to the metric field, you get the Einstein equation in the case of general relativity, or its modification in the case of F-bar theories. It has this rather lengthy expression. The important things to note is that besides r and this function f(r), there is another thing, the derivative of f with respect to r. That's a very important function in this field, in this theory, as we will see. The first two terms are, in essence, a kind of a small modification of general relativity. This third term is actually quite important because it brings derivatives. This is a wave operator, and additional derivatives acting on some function of the Ricci scalar. What is that function? Well, if it's a constant, the function is just minus twice the cosmological constant. So in fact, F-bar theories include lambda Cm. You can add a constant or a linear piece, which is actually rather trivial because a constant r, constant times r, corresponds to a redefinition of the Newton's constant. You just pull out a constant factor multiplying the linear term. That's rather uninteresting by itself, but then you can construct a power series expanding about any point. It may be a Laurent series, it may be negative powers, and a lot of issues involved here, technical issues, which I will not discuss. From this equation, one can plug in the Robertson-Walker background describing a homogeneous, uniformly expanding spacetime and evaluate on the Einstein equations, and what one gets is this modified Friedmann equation from one of the field equations. And I remind you that in general relativity, here's with no curvature, the square of the Hubble parameter would be the density multiplied by 8 pi g. But then there are corrections owing to this f of r. This first correction you can think of as like a cosmological constant, which it would be if f is a constant. But this term is a little different because it involves something like a cosmological constant multiplied by a function of time. I'm sorry, this is not the cosmological constant, it's actually the derivative of f. And then there's furthermore a time derivative. So it's complicated, and as I mentioned last time, for any expansion history h and any density rho, one can find an f of r that solves this equation. Designer f of r theories. I'm going to focus on the dynamics beyond the Robertson-Walker, and I'm going to look at the evolution of this field and its perturbations. And it is important to point out that although this looks like a second-order equation because I have two time and space derivatives here, this f sub r is a function of the Ricci scalar, and the Ricci scalar itself has two derivatives. Remember that in general relativity, the Ricci tensor is constructed using two time derivatives of the metric. Okay? So this h already has one derivative of the expansion factor a. There's another. There's a square quadratic term. Here is a second derivative of one of the potentials, the curvature potential, in the conformal Newtonian gauge. And this prefactor is just the second derivative of this f with respect to r squared. So again, this term, these corrections would vanish if we just had constant and linear pieces in this function f of r. Now, because of this second time derivative, implicitly in this function, remember this is some function of r, and therefore it's a function of the second time derivative of the potential. There are two more time derivatives. The Einstein equations, which until now were second-order differential equations in time for the metric functions, now become fourth order. In fact, the Einstein-Hilbert action is a rather special one, in that it not only is generally covariant, that is, it's an integral of a scalar, coordinate invariant, but also it is such that equations of motion are second order, even though the action is constructed using second derivatives of the metric. Think about a classical mechanics problem where your kinetic energy term was not the square of the velocity, but the square of the acceleration. Write down the Euler-Lagrange equations, and you'll see that you get higher order equations of motion. Only when you have special combinations do those reduce to second order equations, and that's what happens in general relativity. Not so in f of r theories, or in most other modified theories of gravity. They are of higher order. How are we to think about this higher order dependence? Well, one way we can do it is to think of this f of r field, it is a space-time field after all, as being something added to the other fields in the metric, the two metric potentials, for example, and one which obeys a kind of a wave equation. That means we expect to see wave-like solutions of this function. Indeed, I will show you that there are perturbations of this function that evolve as plane waves with a dispersion relation similar to that of a massive field or a massive particle. When this class of theories was first introduced for the R-squared gravity by Starobinsky in 1980, he recognized this higher order nature, noticed the propagation of this field, and quite correctly described it as an extra scalar degree of freedom, like a new scalar particle called a scalaron. And so higher order theories of gravity, even if they are not explicitly scalar tensor theories, if they're just based on the curvature invariance of manifold, typically will have additional scalar degrees of freedom, which you can think of as new particles. So now, let's ask, how would one do the cosmological perturbation theory in such a case? Well, we have these two metric potentials, just as in general relativity, and now I'm going to add perturbations of this scalaron. fact, it's the perturbations which I will call the scale on, the excitations of this field. And so I do the standard trick of perturbation theory, which is to replace a field by its background or zero-Thorda solution, here for the Robertson-Walker spacetime, plus a fluctuating piece. And similarly here and here. Although this f sub r is a function of the Ricci scalar. Yes?
But the idea was to avoid the need for dark matter. And in that sense, you are already introducing the scalar as the dark matter. So,
very important question here. Assertion. The motivation for modified gravity is to avoid the need for dark energy. Yet I'm introducing a new field, the scalaron. It's true. I confess. I failed.
Not only that, but you have to introduce a physical scale with a particular number.
Oh, there are lots of criticisms one can lay against this theory and any modified theory of gravity. Keep those in check, okay? And I encourage you to take the empiricist viewpoint to ask, what could we test? And from that perspective, if these theories make different predictions than, for example, stressed dark energy, it's worthwhile to explore the consequences of these theories. And as I hope you will see, maybe not immediately, but soon, these theories do make distinguishable predictions. So it's very important to ask these questions about why are we doing this? Why are we doing this? Another viewpoint is that to gain confidence in the lambda CDM theory, you want to look at alternatives and ask, can I reject those alternatives? If I can, then I gain confidence in my null hypothesis. Alternatively, you might be a great fan of scalar tensor theories, and Teves, for example, and convinced that this, for philosophical or other reasons, must be the correct theory, and you're going to tweak it until it fits the data. It's up to you. Here's the cosmological perturbation theory. So we do this, and we plug into the Einstein equations, and the result is a big mess. It's a big mess. I'm not going to try to put all the equations up for you, but I just want to show a couple of equations with characteristic features. First of all, I have one equation which, in the case of GR, had this term in the red plus the right-hand side. This is the Poisson equation for the curvature potential psi. It gets modified in the case of f-bar theories in two ways. One is that effectively the Newton constant has changed by a factor of 1 plus f sub r. Where does that come from? Let me back up. One plus f sub r multiplies essentially the Einstein tensor, and if you divide through by that factor, you'll see it redefines the Newton constant. This f sub r may vary with time and space, and so it is a time and space dependent redefinition of the Newton constant. That's rather ugly, but there it is. And if it is dependent on time and space, then just, yes, kind of question. What are?
So I was just wondering about t and tau and your time derivatives at f.r, because you use the t in your...
Yeah, all my time derivatives here are conformal time derivatives, just to be clear. What question?
What are the fourth order derivatives?
Where are they? They're in the never-ending Einstein equations, which is too long for me to put on a page. They're in the spatial parts of the Einstein field equations.
So you have four derivatives, then
But you have only one extra scalar. What's the other degree of freedom? So you have 4 derivatives, so you have 4 independent solutions, right?
Correct.
So then you have only one extra scalar degree of freedom. What about the other one?
Yeah, qualitatively, it's the same as in GR, where, remember, my curvature equation for the curvature potential was a wave equation involving the sound speed of the matter. So the other degree of freedom you can think of as sound waves propagating through the matter fields. This is something I didn't dwell on in the first lecture, but perhaps I should make a remark here. In general relativity, there is, in pure gravity with no matter fields, there is one propagating degree of freedom, or 2 if you count the 2 felicity states of the graviton. Now, if you choose the conformal Newtonian gauge, or its generalization to include vector and tensor perturbations, something called the Poisson gauge, the scalar pieces are like longitudinal gravitons. They don't propagate. They're fixed completely by the matter distribution, classically. So in other words, think of Newtonian gravity as action at a distance. If you say what the matter distribution is now, you know the Newtonian gravity field everywhere now. In fact, the same is true for the scalar mode of this scalar vector tensor decomposition in the Poisson or conformal Newtonian gauge. Now, that doesn't mean that general relativity in this gauge or any other is action at a distance. It's like electrodynamics. If you have studied Jackson's book in the Coulomb gauge, the same thing happens. There's a longitudinal vector potential. Well, it's not a vector potential, longitudinal potential, which obeys a Coulomb equation. Coulomb equation has no time derivatives. It's instantaneous. The electric field of, not the electric field, the Coulomb potential of a point charge is 1 over r, and if you move that point charge, it readjusts instantaneously everywhere in space. Now, does that mean that the electric field readjusts everywhere instantaneously in space? No, of course not, because it has a vector potential as well, whose time derivative has to be calculated. Similar things happen in gravitation. With this choice of gauge, the curvature potential psi and the other potential phi down here basically adjust instantaneously to the matter distribution. The 2 time derivatives that appear in the Einstein equations for this potential in general relativity actually arise from the matter dynamics, from the motion of matter fields. Sound waves propagate through matter fields, and they cause the density perturbations to have second-order differential equations in time. And then the gravitational potentials, the scalar potentials, adjust instantaneously to those. I don't know if I've clarified things or not. I suppose it all depends on your comfort level with the concept of working in different gauges.
One of the things that always impressed me about general relativity is that the equations not only told you what the fields were, but actually told you what the matter distribution was, which is unique compared to others. So does this actually violate that?
No. So George made the point that general relativity, the field equations themselves imply, in fact, the conservation of energy momentum tensor in general relativity. So they imply the fluid equations. You can get those from the Bianchi identities.
But they actually also give you the distribution of matter automatically. The matter.
Yeah, the Einstein tensor constructed from the metric tells you directly the stress energy tensor. That is amazing. Now, actually, general relativity is not unique in this regard.
That doesn't happen for electromagnetism.
It does. It happens exactly for electromagnetism because charge conservation is a consequence of the gauge symmetry, and the first Maxwell equation tells you the charge distribution from the instantaneous electric field. Right? So for any gauge theory, you have these constraints, and for local gauge, for gauge theories with charges, we have these conservation laws. General relativity is more complicated than E&M, but qualitatively it has the same kind of characteristic behavior. Now, when you modify general relativity, you might then worry that you would lose these advantages of general relativity. For example, natural question, natural bar theory, are the equations of motion consistent with local energy momentum conservation? If you take the four divergence of the field equations, will you get that the divergence of stress energy is zero? You had better, because the action that I wrote down requires that. And the answer is, yes, it works out in F-bar theories. So F-bar theories also have this beautiful property of implying, just from the gravitational sector, local energy momentum conservation. But they have some modifications, and as I was starting to explain, in effect they have a time variable, time and space variable Newton constant from this prefactor. You might entertain, while you're on the catamaran, how would Newton's laws change, Newton's laws now, for particles, if the Newton constants are changing with time? I think you would discover that in the Newton equations, suppose you started from a Lagrangian formulation, I think you would discover that time derivatives of the Newton constant would appear in the equations of motion. And that's in effect what's happening here with this FR dot term. Okay? And in this case, those time derivatives, which are evaluated on the background, of course, are modulated by the perturbations of that background, these metric potentials. So these terms, and the 1 plus FR here, all come from this variable gravitation constant aspect. But in addition, there are terms that are proportional to the scaleron. Now, as many of you have noticed, there's no second time derivative of the scaleron here. That occurs in another equation, which is, I'm trying to check I hope Alessandro will help me to get the algebra right on that equation. It's a pretty hideous equation, the wave equation for the scaleron. But the thing to notice is that these terms immediately have some important implications for growth of structure and for gravitational slip. For example, this epsilon enters into the Poisson equation similarly to the curvature potential. Okay, and so it is going to affect the gravitational dynamics of anything in response to symmetric potentials. Moreover, this equation shows that the curvaton field can mimic a shear stress. So one alternative to stress dark energy is a scaleron. And so to test either stress dark energy or a scaleron, one should try to measure the difference of gravitational potentials here. And in my third lecture, I'll explain how that can be done by combining gravitational lensing with the growth of structure. Are there more questions before I continue?
So, how many perturbed equations do you have? And how many do you need to use to solve the system?
One has the same number of equations as in general relativity, basically the same structure. There are extra equations which enforce energy and momentum constraints. In fact, this is one of them. This is a so-called medium energy constraint equation.
So one has more equations for variables to solve.
No, you have the same number of equations, but the equations have more time derivatives, and so you have, as you'll see, higher order solutions. Yes?
Yeah, if you can always talk about the scaleron, it is true that the FFR theories are scalar tensor gravity.
Yes.
And a specific choice of scalar tensor gravity.
I'll come to that momentarily. Just wait a few minutes and then I'll talk about introduced scalar tensor theories and see how they're relatable. Okay, well, I didn't write down all the field equations because they're quite ugly. And solving them, even for something as simple as a W fluid, even for cold dark matter, is an unsolved problem. In fact, it has, to my knowledge, not even been explored in the literature. So Alexandra and I are trying to work that out. Short of having a complete solution, one can look at a kind of a perturbative limit of the perturbation theory, and that is to ask when the scaleron is small, can one solve the problem perturbatively? And I'm sure that the answer to that question is yes. We just haven't done it yet, but we're on track to do it. There is, however, a limit in which the solution is quite straightforward. And that is the WKB limit, where this potential and also the scaleron, all the fields, have modes like this. Plane waves with a frequency omega that obeys the following dispersion relation. This just comes directly from the equations of motion. I won't go through the algebra here. This is written in co-moving coordinates, so that t should be tau. Sorry about that, conformal time. And that's why there's this a squared. And this m sub s is the mass squared of the scaleron field. This has been known in the literature for a number of years, this result. So it's quite interesting. It has the correct units. F sub r is dimensionless. F sub r has units of 1 divided by the Ricci scalar, so this has units of Ricci scalar, which is a frequency squared. Using units in which h bar is 1.
How come that it's not visible time, it's conformal time? Because usually for regular quantum mechanics, it's always.
At the high frequencies of interest here, this a is essentially a constant, so you can absorb it into omega and k and have no change. But yeah, in this limit, it doesn't matter. If one goes to the next order of WKB, it works out how the amplitude varies with time. That one has to be over here. Now, there's something a little peculiar about this. The limit of general relativity is when f goes to 0, f sub r goes to 0, and f sub r goes to 0. That's a singular limit of this system because then this frequency goes to infinity. But there are two additional modes here, left and right, essentially propagating scalars. So what I've just said is that in the GR limit, if you take the continuous transformation of f of r to gr, you end up with this peculiar situation of having infinitely fast oscillations of extra degrees of freedom, which don't show up in general relativity. Infinite mass particles, which are not present in GR. There is, in fact, a classic analogy to this in fluid mechanics. It's called a viscous boundary layer. I mentioned last time about the Navier-Stokes equations. These are the Euler equations of fluid dynamics, but with the presence of shear viscosity. If you have a fluid traveling along a boundary, then in the absence of viscosity, the velocity field can be completely constant within the bulk of space, and even slipping along the boundary. But in the presence of viscosity, viscosity will not permit the boundary condition of a fluid sliding freely on a surface. The velocity must go to 0 through what's called a boundary layer. The thickness of that boundary layer depends on the inverse of the viscosity. And so as one takes the inviscid limit, the Euler equation limit of the Navier-Stokes equations, one gets a solution where the velocity field in the interior of a pipe, let's say water flowing in a pipe, is uniform. But then there's this tiny little skin close to the edge of the pipe where it changes almost discontinuously, changing very dramatically the character of the solution. Similar thing happens here, but instead of the boundary layer occurring in space, it occurs in time. Okay? And there is therefore a key role of initial conditions on the setting of these modes and on the behavior of that. And we still do not know the answer, but it's an interesting question, whether, as in the case of fluid flow down a pipe, there is a singular solution that modifies general relativity. And that's currently under investigation. So to summarize the conclusions about FFR theories that I presented here, there's a non-zero gravitational slip induced by this scaleron. And so certainly we want to measure the gravitational slip and measure other things if possible that would distinguish between a scaleron and stress dark energy. There will be modified growth of structure, that's clear from modifications of the Poisson equation. And the interesting question here is whether those modifications are present, even in the limit as f goes to 0, whether there's a singular limit that's different from general relativity. These theories characteristically have a time-varying gravitation constant, similar to scalar tensor theories, and we will see why in a moment. And then they tell us that there are additional quantities that we'd like to measure, the scaleron being one. Although I have discussed this in the context of FFR theories, these features are quite generic, and they will apply for probably all higher order theories of gravity. And so one should look for signatures like this in data. Now I want to turn to the question of that was implied about scalar tensor theories. It is another way of thinking about these FFR theories. One can redefine the variables used in the action. For example, taking the metric and redefining it, calling it G tilde with this combination. One can introduce a field phi, which is related to this FSR. In fact, we might even call this field the scaleron. And one can introduce a potential. Take these as merely redefinitions of fields in an action. We can change variables, changing here the dependent variables of our problem. And if you do that, the action in these new variables takes the following form, where the gravitational piece now is the Einstein-Hilbert action. In these variables, gravity is not modified. That's very interesting. You can have a modified gravity theory that, viewed through another perspective, is not at all modified. What is happening? Well, two things. First of all, you've had to explicitly introduce another field, this phi, and you could take my word for it, check it as a lengthy homework exercise. This will exactly reduce back to the other action in the transformations I showed. This looks like a standard scalar field with some potential and a kinetic term. This could be like an axion or an inflaton. But there's one rather unusual modification, namely that the metric appearing in the matter action is no longer the metric that obeys the Einstein equations. What that means is that the matter no longer moves along geodesics of this G tilde mu nu metric. In other words, there will be deviations from, let's say, Newtonian gravity or geodesic motion involving derivatives of this f sub r, this scaleron. Those deviations are sometimes called fifth forces. Now, if you haven't seen this before, or even if you've seen this a few times, you probably are scratching your heads. How can there be a fifth force if we started with an f of r theory where there is no fifth force? These different ways of looking at a theory are called, rather badly in the literature, different frames, conformal frames. They're not just frames of special relativity. In special relativity, when you change frames, you are changing coordinates. You're changing the space-time, the way you label points in space-time, but you're not changing the fields defined on space-time. You have an electromagnetic field, you haven't redefined that. You have a Riemann tensor, you haven't redefined that. In this case, we're not changing the coordinates, we're actually changing the fields on the coordinates. And the two cases that I've presented for the F-bar theories are called Jordan frame and Einstein frame. Einstein frame is the tilde one, where the gravitational action is the Einstein-Hilbert action. Now, it's very important, this last point, that despite the very different appearance of these formulations, the predictions for physical observables are the same. They're independent of the frame. And I won't have time to show that to you, but the references that I mentioned at the beginning of the talk will guide you through that if you haven't seen it before. So let's take seriously this idea of having a new scalar field introduced and ask how can we modify the action in other ways. Maybe there are other different kinds of modified gravity theories. Well, there's a class called scalar tensor theories, which modify, in the Jordan frame, the Einstein-Hilbert action, typically by multiplying by some function of a scalar field, and this is a classic case, the Brand-Sticky theory, going back more than 50 years. It has a constant parameter omega. This is a theory that was introduced as an alternative to general relativity when measurements were started to test general relativity on solar system scales. And it's the Jordan frame because the matter fields couple directly to the metric, so matter moves along geodesics, but the geodesics, the Einstein equations are going to be modified by this scalar field. And here are the Einstein equations with the scalar field. Notice that the Newton constant is redefined, just as we saw for the FMR theories. And there are extra terms on the right-hand side, which you can interpret as the stress energy of this scalar field phi. Oh, there should be a box, a dental inversion operator multiplying this. This is a wave equation for that scalar field. And it so happens that in the solar system, we know that G doesn't vary much in time or in space. For example, from many different observations, from lunar laser ranging, from spacecraft ranging, from the Cassini spacecraft most recently, we know that this Newton constant is really constant to a high accuracy across the solar system. That implies that this phi has to be constant, and there is a down inversion box multiplying this, so that the box of phi is almost zero. That implies this omega has to be extremely large. The Brand-Sticky parameter has to be greater than 40,000 based on the Cassini limits in the solar system. Okay, so basically this phi field just freezes out in its dynamics. Okay, that's the bulk of what I wanted to say today. So I've discussed F of R theories. I've talked how they're related to scalar tensor theories. I talked a little bit about the cosmological perturbation theory in the modified gravity theories with a focus on F of R theories. I think I will not go into that subject next time for scalar tensor theories. But there is one aspect that I will comment on, and that has to do with the Birkhoff theorem and the fact that physics on small scales, for example, in the solar system, in general relativity, decouples from large scales in the universe, but that is not automatic in these modified theories of gravity, because the famous Birkhoff theorem of general relativity is violated in F of R theories. And so I will remark on solutions to that problem, which go under the name of, help me, I've just forgotten now what it's called, the chameleon mechanism. And so F of R and scalar tensor theories, which have a chameleon solution, can, in principle, satisfy solar system constraints of gravitation, as well as having interesting modifications on cosmology scales, and that makes these quite interesting theories to explore. There are many papers on this in literature. I may or may not touch the Tevis theory, tensor vector scalar theory of Bekenstein, which is a Lagrangian-based implementation of modified Newtonian dynamics. I think I'm going to call for a vote of the audience whether to spend any time on Tevis or to devote the bulk of my third lecture to something that's a little closer tied to observations, which is cosmological scale tests of gravity, and especially of the gravitational slip. So I will stop now and take questions, and I'm also going to ask for a vote on Tevis. Thank you.
Or comments or questions? Marcelo,
Okay, so I'd like to make some remarks about. First is about the extra degree of freedom. You can see the extra degree of freedom as another polarization mode. So you can have, besides the plus and cross polarization modes of gravitational waves, you have the breathing mode, which affects the matter isotropically. So that's one way of seeing things. Another way of seeing things is that if you see the original theory as for order, then you need more initial data for the second and third time derivatives. And the other remark is that you have to be very careful when you make the identification with scalar tensor theories, since Luisa remarked in her talk yesterday, the scalar field potential could be ill-defined. So in order just for the scalar tensor theory to work, the potential that arises should be single value, and that doesn't happen for every FR model. Okay.
Thank you very much. Just to comment on your first comment, the idea of the breathing mode, that would arise, for example, for a massive graviton, which would have a longitudinal mode. This is different. This is not a longitudinal mode of a massive graviton, because the spin-2 graviton here is still massless.
Another question.
I know you said you might talk about this in your next lecture, but I was wondering if you could elaborate on the comment that the scalaron drives gravitational slip. You didn't really say much about that. So I was wondering if maybe you could define gravitational slip and then just say a little bit about that.
Gravitational slip in literature is the difference of these two potentials, or if we use the Hu and Sugiyama convention, it's the sum of the two potentials. So beware of different conventions in the literature, and also different sign conventions. But basically, it's the combination of the gravitational and curvature potentials, which in general relativity can only be a source that is produced by shear stress. The scalaron here directly provides a source of the difference in these two potentials. Now, to evaluate that, one has to indeed work out the full dynamics of this scalaron, and we definitely have not done that. So I cannot tell you how big this is. My goal would, in fact, be to start out with initial conditions for the 4 different modes, 4 sets of combinations of variables, work out any necessary physics of this boundary layer in time, having to do with the initial conditions, and then have a predictive way of determining the amplitudes of this scalaron at late times. That remains for the future.
More comments?
I don't agree with your comment. Even if you have a massless scalar field, you can have a breathing mode. That happens in scalar tensor theory. If you don't have a potential, you can have a breathing mode.
Okay, we should talk about it afterwards.
You can have a breathing mode, but it's not a polarization. That's what I was saying. Well, it depends on what you call polarization.
Well, it's another scalar degree of freedom.
It is. Just give it this mode. Even if it's massless, you go this mode.
Well, sure, it has monopole oscillations, but that's not all that it has. course, its oscillations have to be longitudinal because it's a scalar. There's no deep significance there. But it is not the same as a massive graviton. It's not the same as, for example, Kurzweil gravity. Will you talk about that, Mark, at all?
Probably not. Maybe a little bit.
Let me take a vote of hands of those who would be interested in hearing about the Tevis theory. Okay. The alternative is to have more focus on the large-scale structure tests of structure formation and gravitational stuff. Okay. Did you know? Good. I can relax a little this afternoon. All right.
We have here another question.
You will electrons vote? I'll see. Maybe I'll give a very brief overview, but I won't talk.
You mean the electron vote?
No, I can't.
Ed, and here is another question.
Hi, I'm under the impression that, in general,